The universe is filled with light, from the brilliant glow of stars to the faint, ancient background left over from the Big Bang. But what if there's another kind of light, one we can't see at all, mysterious shadow of the photons that let us see everything? Scientists call them dark photons. They might be the key to solving one of the greatest mysteries in physics, the mystery of dark matter. Everything we see, stars, planets, you, me, all the galaxies in the cosmos, makes up less than 5% of the universe. A staggering 85% of all matter is something else entirely, something we call dark matter. We know it's there not because we can see it, but because of its immense gravitational pull. Galaxies spin so fast they should fly apart, but they don't. An unseen mass provides the extra gravity needed to hold them together, shaping the very structure of our universe. This invisible substance doesn't emit, absorb, or reflect any light, making it completely transparent to our telescopes and our eyes. It's a cosmic ghost, present everywhere, yet fundamentally disconnected from our world. Let's first look at the puzzle. Let's first look at the world we know. In our everyday reality, light is carried by a fundamental particle, the photon. These tiny packets of energy are the messengers of the electromagnetic force. They are the reason you can see the screen in front of you, the reason solar panels generate power, and the reason the cosmos shines with the light of a trillion suns. Photons interact with charged particles like electrons, allowing them to be absorbed, emitted, and detected. They are the fundamental carriers of information in the visible universe. Now imagine there's a hidden, parallel version of this force, a shadow of electromagnetism. If our universe has photons, perhaps the dark universe has its own messenger particle. This is the idea behind the dark photon. It's a hypothetical particle that would carry a dark electromagnetic force, interacting not with our familiar matter, but with dark matter particles. Just as a normal photon wouldn't interact with an uncharged particle like a neutron, a dark photon would pass right through us, our planet, and our stars as if we weren't even there. It would be the exclusive messenger for the dark sector, a hidden realm of particles and forces that mirrors our own. So why is this idea so important? Because it could finally explain how dark matter behaves. While dark matter doesn't interact with us, it clearly interacts with itself. We see it clumping together to form vast halos around galaxies, providing the gravitational scaffolding for cosmic structures to form. A dark photon could be the very reason for this clumping. It would provide a way for dark matter particles to talk to each other, to attract or repel, allowing them to form the complex structures we observe indirectly. It would be the bridge that connects the seemingly inert nature of dark matter to the dynamic structured universe we see. Finding it would not only solve the dark matter puzzle, but also potentially unify the dark sector with the known laws of physics, revealing a deeper, more complete picture of reality. But how do you find a particle that's defined by its invisibility and its refusal to interact with our world? The search for dark photons is one of the most ingenious and challenging quests in modern physics. Scientists are tackling this problem from multiple angles. At massive particle accelerators like those at CERN, physicists smash beams of particles together at nearly the speed of light. They're looking for a phenomenon called kinetic mixing, a tiny, subtle bridge where a normal photon could momentarily transform into a dark photon before decaying into particles we can detect, like electrons and their antimatter counterparts. It would be like a flicker in the data, a whisper from the dark sector leaking into our own. Meanwhile, other experiments are listening for fainter signals. Deep underground, shielded from cosmic rays, experiments like LUX-Zeppelin are designed to detect dark matter particles directly. While their primary goal is to spot a dark matter particle bumping into a normal atom, they're also sensitive enough to potentially detect the subtle energy shift caused by the absorption of a dark photon. Other experiments, like a DMX, use powerful magnetic fields and microwave cavities to try and coax dark photons into converting into regular photons, producing a faint telltale radio signal. Astronomers are also joining the hunt, scanning the skies for unexplained gamma rays or radio signals from deep space, which could be the signature of dark photons annihilating or decaying into light we can finally see. What if they succeed? What if dark photons are real? The discovery would be nothing short of revolutionary, would fundamentally reshape our understanding of the universe and its forces. We currently know of 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. The existence of a dark photon would prove there is at least one more a fifth force of nature, operating in a dark mirror world that coexists with our own. This hidden world would be connected to ours only through the most subtle and fleeting interactions, a cosmic secret that has been hiding in plain sight all along. It would open a new chapter in physics, providing a bridge between the visible cosmos and the vast dark universe that has eluded us for so long. The universe might not be silent after all. It could be filled with invisible light, a hidden symphony of dark photons playing out on a cosmic scale just beyond the limits of our perception. Dark photons remind us that reality is far deeper and more mysterious than what our eyes can command, that every new mystery we solve only serves to reveal another, more profound layer of wonder. So, the next time you look up at the vast, star-dusted night sky, remember, there's so much more out there than just the stars. There's an entire unseen universe, a dark cosmos, and we are only just beginning to learn how to tune in. No magic, just physics.
Stay curious.